have our 12 nanocoulomb charge distributed uniformly along the y-axis from y equals 0 to y equals 4. So basically you can think of it as a nice thin line of charge between 0 and 4. There's a total of 12 nanocoulombs of charge there. We want to know the x component of the electric field at x equals 2 meters on the x-axis. So if we draw our axes, here's our y-axis, here's our x-axis, our charge is between y equals 0 and y equals 4. We want to know the value of the electric field a distance of 2 meters away. That's x. So each piece of this rod is going to contribute to the electric field at that point. This one would create a field that way. Since it's a positively charged rod, it points away. If we look at a piece up here, it creates an electric field that way. So our distance r is changing. Our direction is also changing. So the distance vertically here we'll call y. The reason why r is changing is because y is changing. This horizontal distance x is not changing. So our three pieces we need to figure out: the dq, the r hat. dq, well, we know there's a total charge of 12 nanocoulombs. So this is q. We know there's a total length. The total length of this is 4 meters. That has to equal the charge, any chunk of charge over the length of that charge. We're going to call it dy since it's along the y-axis this time. So dq will be q over L dy. Okay, so r. R is the distance from the point we're interested in to whichever one of these charges we're looking at. R is changing, so r cannot be a number. R has to be in terms of our variable y. So using the Pythagorean theorem, square root of x squared plus y squared is r. R hat, there are both x components and y components. We only want the x component for this problem. So I'm only going to look at just the x component. The x component is right here. It's adjacent to our angle, so it will be the cosine of theta. This theta, where is this theta in this triangle?
On the x-axis.
Right there. So the cosine of theta, if we look at this triangle, cosine is adjacent over hypotenuse, so it'll be 2 meters over r, which is the square root of 2 squared plus y squared. So that's our x component. There is a y component. We just don't care what it is for this problem. So our electric field, plugging it in, integral of k, our constant, times dq, which is q over L dy, over r squared, which is the square root of 2 squared plus y squared, times r hat, which is 2 over the square root of 2 squared plus y squared. Limits of integration. The limits of integration need to basically state the boundaries of the rod.
I think it's square your r.
Oh, thank you. Thank you, thank you.
Do we keep the negative?
What negative?
Oh, that was for x.
So what are our limits?
0, 4.
0, Lower end of the rod is at 0, upper end of the rod is at 4. So pulling out the constants, the K is a constant, Q over L is a constant, the 2 is a constant. That leaves us with the integral of dy over the quantity of 2 squared plus y squared to the 3/2. This integral, on the integral table, just think of your x's as y's, because your y is the variable, the 2 is the a. So let's see, this one is this. So plugging in the numbers, K 9 times 10 to the 9th Newton meters squared over Coulomb squared, or 8.99 times 10 to the 9th. Either way is fine. Our total charge is 12 nanocoulombs, so 12 times 10 to the negative 9 coulombs. Our L is 4 meters. You can multiply that by 2. Technically this 2, since it was this axis, it has units of meters as well. So that had units of 2 meters. Plugging in our limits, we're going to put 4 meters in for y. 2 squared is 4, square root of 4 plus plugging in for y, the 4, so 16, minus the lower limit, conveniently enough, is 0. So unit-wise, we have meters squared on this side. These meters canceled. That coulomb cancels with one of those. These meters squared cancels out with the meter squares that are in here. These were all, y's and x's were all meters. So plugging in and chugging these numbers through, we get 12 newtons per coulomb. And it's the I-hat direction. It's only the x component. That's kind of implied in the problem, though. You don't have to have the I-hat on it. So you have to leave R and R hat if they're changing with each little piece of charge. So think about, if you look at a couple different pieces of charge along the rod, if R and R hat are going to be different, then you need to write them in terms of the variable that's changing. So they're not going to have a numerical value. You need to write them as variable and keep them as variable until you have done the integration. Questions?